And now this is going to be the limit as n goes to infinity of pi over n over sine pi over 2n times cos pi over 2n minus cos, this is just an awkward expression, 2n plus 1 pi over 2n. So the product of limits is the limit of the product. This, if we let pi over n be theta, this is, as n goes to infinity, this is going to, right, pi over n is going to 0. If theta equals pi over n, the limit as n goes to infinity is like taking the limit as theta goes to 0. And the limit as theta goes to 0 of theta over sine theta is 1, right? I'm using that fact right now. Yes, sir?
Isn't that supposed to be a pirate square?
Yes, it is. That was this 2 that you so kindly advised that I can take out for you. Yeah, that's right. Just didn't write it. Absolutely. The limit?
Yeah. I don't know if is that a number.
This? That's a
No.
this.
Right.
This.
Right. That limit n goes to a pi over 2n later.
Sine.
This is sine. Oh.
Sine pi over 2n. It's okay. So letting theta be pi over 2n as n goes to infinity, theta goes to 0. And we know from Calc 2 that that's 1. So this limit is 1. What's this limit? It would be cos, it's a continuous function, cos 0 minus cos pi, right? That's 1 minus 1, that's 2. So the product is 1 times 2n. So the limit as n goes to infinity of the Cauchy sum is 2. So that is a Cauchy integral that we have done by, not by anti-differentiation, but by summation, right? So that's 2.1.1. Everybody okay with that one? All right. Let's look at Stirling's formula. After all, it's a Stirling result, right? Can I move this? I'm gonna. If I move it too fast, let me know. Are we okay with this? Okay? All right. Stirling's formula, which is, by the way, back in the good old days, before you had computers and calculators, if you needed an estimate for n factorial for large n, even for middling n, n factorial is approximately equal to the square root of 2 pi n times n over e to n. That's Stirling's formula. It's an asymptotic approximation for n factorial. You know the difference between absolute error and relative error? Its relative error as n goes to infinity is 0, but its absolute error is infinite. Right? If you're using g of n to estimate f of n, then the limit as n goes to infinity of g of n over f of n, if that's 1, then it is relatively error-free, right? But if you take the same limit operation, delta of n, say, is the absolute difference between the two. This can trundle off to infinity while that stays at 1. So the relative error is absent, and the absolute error is infinite.
I haven't actually played around with the numbers on this one, but I
just from playing around with factorials. And you calculate a factorial, obviously, if it's big enough, 10 factors into it, 20 factors into it, 30, and so on. The end of the factorial is going to have a whole string
Lots
of
of
zeros.
zeros.
Yeah.
Oh, as you pick up the multiples of 2 and 5.
Yeah.
Yeah, factorials eventually tend to have arbitrarily many zeros. That'd be a good Putnam question. What's the smallest n for which n factorial has 2,000? What do they always have a problem that relates to the year? 2,009 zeros. So you'd have to pick up the first 2,009 factors of 2 and 5, right? So you hit the factors of 2 more often. So it's when you got to the 2009th factor of 5 that you would have it. I'm just thinking out loud here.
2009.
Yeah, you go 5, 10, 15, 20, and you go out. You go, that's not really as hard, too hard, is it? It'd be 5 times 2,009. 11,040 or 10,045. I think 10,045 factorial is some huge number of digits, and then 2,009 zeros after it. Because you would have 2,009 fives.
I think it should be 1,000, not 10.
Did I screw that up?
Well, if you're talking about 2,000 multiplied.
Oh,
Yeah. Yeah, that is right.
5 times 2,009. Unless I've lost, it's entirely possible I fried myself with the paint, but I do think that's 10,045.
That is good.
So that's going to have 2,009 zeros. That is the smallest factorial that has 2,009 zeros at the end, I claim. Do we believe that?
We just have the factors of 25 or 25.
I picked those up, don't I? Oh, wait, no. For 25, we get 2 factors of 4. Oh, Christ. So what we have to do is go through this and figure out all the powers of 5 that show up and start knocking this down a little bit. Like since I go past 25, I reduce it by 1. I go past 125, I take down 2. I go past 625, I take off 3. So I do that until I get up past this number, right? Then I stop doing it. That accounts for the multiple 5s. And the 2s I'll hit long before then, but I need the 5s to get the 0. The 5s control, right? That would be a good fun. We should send that. Huh?
Yes, that's good.
That's a good problem. Make a note of that. All right. So this is the difference between absolute and relative error. So the statement, Stirling's formula is a statement that the limit as n goes to infinity of n factorial over square root of 2 pi n over e to the n is 1. In other words, it is relatively error-free. But the absolute error becomes infinite. And Stirling, another, not a contemporary, he was more of a contemporary Euler than Newton. Euler was, 30 years of overlap. Developed this formula. So let's have a go and see if we can. I tried this at home. Don't try this at home. And I screwed it up. So let me try it here with your help. I think I can get past the hard part, but I fell asleep actually before I got the last part. Evaluating the constant, this little thing that did me in.